So our final speaker for the morning is Dr. Jelena Mirkovic. She is a research associate professor and researcher in Network and Cybersecurity Division.
Thank you. Hi, everyone. So I'll talk today about our work on modeling student learning on network testbeds. And this is joint work with colleagues from Lewis and Clark College and Evergreen College, and it's funded by the National Science Foundation. And OK, so many classes in CS and EE use active learning to help their students get more engaged with the material and to better retain knowledge that they get in class. And active learning here means usually assigning homeworks and lab exercises that exercise some concept taught in class. For example, if the class has taught the student about routing, then the student could be asked to set up routing in a small network for a homework assignment. And these assignments are usually given on network testbeds or clouds. We have a network testbed at Marina Del Rey at ISI, and it's called the TerLab testbed. It's helped 15,000 students over 15 years of existence get educated in networking and cybersecurity, and 200 classes have used the TerLab in education. And most of these classes have used shared exercises that we have developed under another NSF-funded effort. So testbeds overall are really good for education, but they are also sometimes challenging. And they might be challenging because students lack some practical skills to complete the exercise. So they might understand the material taught in class, but they just don't have these practical skills to successfully complete the exercise that becomes part of their grade. And those skills could be Linux-based skills, or how to use SSH to connect to the testbed, or how to use terminal-based interaction as opposed to a graphical interface, or how to deal with the distributed nature of the exercise, such as working with multiple nodes at the same time. For example, the student might be asked to find a buffer overflow in an application, patch that buffer overflow, and submit a patch. And the student might understand what a buffer overflow is, but they just have never found it in an application, so they don't know how to go about this task. Students get these tasks usually for homework assignment, which limits their opportunity to ask for help, and teachers are usually unaware that students need help until the homework is submitted and graded. By that time, it's already too late, and so the testbed might become a deterrent as opposed to helping students get better knowledge. We would like to address this problem by developing automated tools that help teachers to track their student progress as they are completing the homework exercise, and identify students that need help and identify tasks that might be challenging for the entire class. And so how do we identify a student that needs help? There are multiple approaches. One simple approach is if we have a structured list of tasks that the student needs to complete, then we can monitor the student's actions with the testbed and compare it with this list of tasks, and we can be very accurate in understanding whether the student completed the task or not. However, this approach is a little bit limited, because if we don't have this structured list of tasks, then this approach does not apply. So there are other approaches that we can take. One is looking for signs of frustration. Is the student typing the same command over and over? Are there big gaps between the interactions? Another approach is looking for outliers, looking for students that take much longer to complete certain tasks than other students, or just engage with the testbed more often or very rarely. Another approach is using machine learning. If we don't know what the students should complete, but we know that all class is working on the same set of tasks, we can cluster their actions and look for students that do not cluster with any group as possible outliers and possible students that need help. And so these techniques range from most accurate to least accurate, but most applicable technique, such as machine learning. And so in our work, we started with the simplest approach, where we have the structured list of tasks, and we monitor everything that the student does with the testbed. We capture terminal-based interaction. We capture everything that the student types and everything that they see on a screen. And we capture that for multiple machines in an experiment that they engage with. And then we merge this into a single log for each student. And we have the structured list of tasks. We compare every action that the student took against this list of tasks, and we annotate the action as either successful or failure fail to complete the task, or unrelated to a given task. And over these annotations, we can then produce summary reports that help teachers identify students that struggle. So one report that we produce is a measure of student effort, how much the student engaged with the exercise. And these are homeworks that usually are assigned for a week or 2 weeks at a time. So the student might take a long time to complete, or they might complete it in one sitting. And so this is a sample homework. For 2 classes, you see that most points are clustered within these 2 days or 2 to 3 days of engagement, and about 300 input lines that they have typed on their terminal. But there are some outliers. So there are students that do not engage well. They take much longer. They are shown in the blue rectangle, and they actually interact very rarely with the testbed. The number of their actions is much lower. There are students that have on-off engagement that are in the yellow rectangle. They take even longer time. They take almost 2 weeks, and they produce certain number of actions with the testbed, but they just take such a long time that they might need help. They might be facing some obstacles. The other thing that we can measure is student success. So remember, each action is annotated as either successful or failed attempt to complete a task. So we can produce this graph that shows how many milestones each student has met over how many attempts they had. And we can see that there are some students outlined in the blue rectangle that have low effort and low success. They really didn't make enough attempts to succeed on the exercise. There are some students in the yellow rectangle that made quite a few attempts, much more than the majority of students, but they are still failing to complete more than half of the milestones. And so these are the students that would merit from teachers' help. Here's another report that we produce. This shows the success rate for each milestone for the entire class, and these are 2 classes shown. As you can see, they have very similar success rates on those 7 milestones, and milestones 1, 5, and 8 are particularly challenging. They have very low success rate. And so the teacher seeing this might conclude that this is fine if milestones 1, 5, and 8 are learning goals. They are supposed to be hard. This is something that students have to try over and over until they succeed. Or the teacher might have expected that these are very easy tasks, and seeing this informs the teacher that they have to cover this for the entire class, maybe in another lecture. Finally, we can help detect common error patterns. So the exercise that I'm showing here, the topology on the left, shows 4 machines, and the students in this exercise are asked to type certain commands on certain machines and find the arguments and the parameter values to complete a given task. And those commands are shown in the blue on the screen. And so we can, by analyzing student actions, we can produce the bottom figure that shows the frequency of each command that is typed on each node. And as we can see in the red circles, there are certain students that are confused where they should type each command. So for example, flutter command should be typed on the attacker node, but quite a few students type it on the client node or the server node. And so this is the case where the students are confused by the distributed nature of the testbed. We can also detect cases where students do not understand how to properly select arguments for commands. And so this is shown on the top right, where we show one command and there are 6 arguments. Actually, all 6 arguments are necessary for that given command, and the students have to also discover the parameter values to go along with these options. And based on the frequencies, we can tell that very often they use 1 or 2 arguments. They don't use all 6, and that's the source of frustration. That's the reason for that milestone not to be met. So to conclude, the system we've developed, Excel, offers automated measures of student progress on well-structured exercises. And we have released our tools publicly on the GitHub site for our lab. We also have the SIGSI 2020 publication describing this work. The monitoring of student actions and the annotations are currently deployed on the TerLab testbed for all classes, so all teachers can benefit from our work. And our future directions are that we would like to see how our tools can be actually useful for research users on testbeds. So one possible application we see is by capturing user input as they interact with the terminal and with their experiment, we can help users automate tasks that they have once successfully completed in manual fashion. And so we can help them scale up their experimentation. The other possible application is by using machine learning, we can identify common tasks that researchers do on the testbed, and we can possibly identify researchers that struggle with a given task and offer them a solution that another researcher has found for a similar task. So thank you for your attention, and I'll take any questions.
Hi, Jelena. Wes Hardiker. I think this is a fantastic effort. I thought for a long time that the education needs to be measured better and turned on its head. So I think that you have a lot of promising results here. I have one question about ground truth. Like, how did you figure out that frustration in your measurements actually matched frustration in a user as opposed to a measurement? So let me give you an example, right? The low success rate, low effort rate could actually be somebody just frozen and not typing, not doing things because they just don't know where to go, versus somebody that really just didn't want to put in the effort.
Right. So we have ground truth for what they should do. So we know exactly these are well-structured tasks. Then we know exactly what they should do. So for every attempt, we can say whether it's success or failure to meet a given milestone. The signs of frustration that I was mentioning and the effort measure are more the sign for the teacher, how much the student is engaging with the exercise. So sometimes the students might not be facing difficulty, but they are not engaging well. And in my experience as a teacher in the past, if you go to the students as they are in the middle of the homework, so in the middle of those 2 weeks, and tell them, I know that you haven't started working on this exercise. Is something a problem, or do you just not have time? You know, it's time to start. It helps push things along. What we don't want to do as teachers is get the homework and go like, oh, well, the student just lost 10 points for nothing.
Andrews, actually.
Oh.
So have you considered doing something similar, say, with Jupyter notebooks, where, say, people are learning data science, and you can sort of track what they type in the cells, and then sort of deploy this in a sort of much wider setting?
That's a great suggestion. That's definitely where we want to go in the future. We started here because this is the pain point for us. I have a lot of teachers that use these materials, and I want students to actually like their testbed experience. I don't want to turn them off just because they, for example, don't know Linux.
Hi, Alexei. I was wondering if there's any technical way to have an accurate measure of time spent on the assignment. Right, your x-axis. So if the student just logged into the server, you can measure login time, but that's probably going to be inaccurate because they're playing Warcraft at the same time. So is there any way that the student could install something on their machine or something that could track time spent accurately? Thanks.
Right. So actually, the time I was showing is the overall time they spent to complete this exercise. But you're right, they didn't work all the entire 2 weeks. We actually have timestamps for every action, so we can tell you how much of the effective time they have spent on the test bed. That's another thing that we can produce. Okay, thanks.